I finished all of it except part A and B for 9, but I did part C because it was
So
easier.
9.
9,
I
it like
was
shows you kind of how to do. Oh, it shows you how to do it, but there were so many steps that I was like, I'm gonna go to the last one.
well, I was confused because it's like repeat the example and then you go down to figure 10.26 and it
Mm,
has an A and a B. I'm like, wait, what? So I got confused there, even though I found the example.
yeah, I did A, B, and C because it has A, B, like it printed off how they did it for that problem A, B, and C.
Oh, okay. So that's what.
Yeah, it's like the last 2 pages. I don't know if you printed them off or not because they like look like a photo out of the textbook.
I was wondering where these came from.
Yeah. It was like the last 2 pages, but I doubt many people printed them because it doesn't look like it relates at all. Like the
Well,
first time I looked at it, I thought it was like the table saying like this is what you use for this shape. This is what you use for this shape. So
that's what I thought, but
yeah, exactly. So
it.
I
I
haven't printed
just
it up,
printed.
so we can work on it.
Sweet. All right. I
Yeah.
don't think it'll be too hard,
I don't
and
think
only.
either. I think it's just a lot of like following the steps to change your equations.
Yeah. So we can pretty much use the same numbers until we get to the part of whatever the RPMs convert to and the radius.
Yeah. All right. And then the only other thing I don't have is for number 1, the very last one, impulse. I have all the rest, so I'll just ask you what you got. But for acceleration, I did angular acceleration. Force, I did torque. Mass, I did momentum of inertia. Work, I kept the same. I don't know if you have to change that one or not.
Wherever I looked, it just said work.
Okay. All right. And then for translational kinetic energy, I said rotational kinetic energy. And then for linear momentum, I said angular momentum.
Impulse, I said angular impulse.
Oh, I guess that makes
That
sense.
that's what I found.
Yeah.
Uh,
Because
so
everything I saw was just like, it just said impulse again, but I read the textbook and it kind of talked about, like, it talked about impulse barely, but it didn't refer to it really as another name. Like, I think it mentioned angular impulse like once. And then from then on out, it was just impulse. So I thought it might
I
be like
had to look it up.
work and impulse and impulse. Oh, you did?
I had to look that one up, but it's either impulse or angular impulse. I don't think it really changes all that much,
Yeah,
really.
I don't think it does either. All right. What did you do for 2A?
So for 2A, since we were looking for the angular acceleration,
Mm-hmm.
I still use the basic formula for acceleration, just its funky letters.
Yeah.
And so we have um, the -7 on the acceleration area
Mm-hmm.
equals the angular acceleration times 0.28, the radius.
Yeah, so did you divide the -7 by the 0.28?
Yes,
Okay, so I did that and I got -25 radians per second squared.
that's what I got.
Okay. For B, I did the equation W2 equals, or W squared equals WO squared plus 2A theta. And then for W2, I put in 0 because it came to rest. And for W0, I used the 95 radians because that was the initial velocity. And then the 2 multiplied by the 25 from the previous example. And then that gave me 181 radians. And then I converted, I divided that by 2 pi to get the rotations instead of radians. So I got 28.7 rotations.
That's
Or
what I got.
revolutions, I guess, is what it's called. Let me change that. That's what you got?
That's what I got. 28.7 revolutions.
Hey, have you done the individual exercises yet?
No, I haven't.
Okay, never
I'm
mind.
not excited either.
I did the first one. Well, I started on the first problem and I got like part A, and then part B I couldn't get. And I emailed him and he was like, oh, just do it this way. So I did it that way and it's still wrong. So
What?
I know. I was like, forget it. I give up. I don't want to do it anymore.
Oh my
Actually,
goodness. The last one last week, there were about 3 that I started working on, and I used every single equation I could figure out.
last week I literally only finished 2 problems.
Really?
I could not do them. I don't know. I couldn't do it. That and I like didn't give myself enough time that week, so it was like I was already rushed. But I could only get 2 problems. I was so mad.
I tried doing all of them, and I couldn't get them. I had to call up my brother, who's a chemical engineer, for his help.
I need my brother to be a chemical engineer. Yeah.
I'm
They were
happy that he
hard
is
last
one.
week.
What?
They were hard last week. I lost my A last week because of that homework. Because it was like
Oh,
I couldn't do anything with it. So hopefully I
so
get it back this
close.
week. Probably won't. It's probably
I
gone.
think the exams are home taken.
Yeah, that is nice because they're easier. And I feel like he's a pretty generous grader.
Yes, unless it's Maple TA.
Yeah. Yeah. All right. For C, I use the equation W equals WO plus AT. And so I solved for T and I got 3.8 seconds.
Same here.
Okay. And then let me erase this. For the next equation, I use the theta equals x over r equation. I rearranged it so it's x equals r theta. And then I did 0.28 multiplied by the revolutions. So I got 50.7 meters.
Yep.
And then for E, I have the W equals R over V. I rearranged it so it's V equals WR. And then I did 95 multiplied by 0.28 and I got 26.6 meters per second.
Same. I like how it's simple this time.
Yeah.
For the most part.
And then for F, I just said yes. I'm like, I don't know, is what I got. So hopefully.
I know. It's like, do these seem reasonable?
Yeah.
We calculated it.
Like, I use math. I think I used it correctly. All right. What did you get for 3?
Okay, so for 3, I had to rearrange a bunch of the equations
Mm-hmm.
so I took the equations for the linear kinetic energy, linear potential energy, and put it with, first I rearranged those so you could get the height alone.
Mm-hmm.
So H equals V squared over 2G for a linear height.
Yeah.
And then I did the same with the rotational, but this time I included the solid sphere where the I is for the
Okay.
inertia. So with that, kinetic energy equaled 1/5 mv squared to make like terms.
Okay. You went way more. I just said the rolling ball will go higher because that is rotational energy and translational energy. So I think we'll be using your number 3.
Okay.
Because mine was not that good.
It's all good. I also said it to go higher, so.
Yeah. Okay. For 4A, if the drive chain exerts a force of whatever on a radius of 5, what's the angular acceleration? So first I determined the torque, so I did T equals FR. So 2200 multiplied by 0.05 because I made it meters instead of centimeters. And I got 110 newtons per meter. And then I did the equation for inertia, which is the m, and then in parentheses r1 plus r0 squared over 2. So I did 12, so it's like the inner and the outer radius. So it's 12 multiplied by 0.28 plus 0.33 squared. Both of those are squared. And then divided by 2. And I got that my inertia is 1.124 kilogram meter squared. And then I plug that back into the equation where it's torque equals inertia times the acceleration. So I did 110 divided by the 1.124, and I got 98 radians per second. Or I guess it's 97.9 radians per
Yeah,
second.
if you do significant figures.
Okay. How'd you do
Which
B?
sometimes. So B was basically the acceleration equals the angular acceleration times the radius.
Yeah, that's what I did.
And so I did 97.9 times 0.33. So the tangent acceleration, not going to try that word, equals 32.3 meters per second squared.
That's what I have as well. And then for C, I did the W equals acceleration times time. So since my W is that 80 radians per second, I divided that by the 97.9, and I got T equals 0.82 seconds,
Same.
which seems a little fast to me, but if you got it too, then I think it's right.
How long?
Okay. All right, how did you do 5? Because on this one, I combined 2 equations, and I'm wondering if I did it right. Well, 3 equations.
So let's see. So the equations that I used, I kind of probably skipped a couple steps, but I used the kinetic energy and the potential energy. But for kinetic, I did the 1/2 mv squared plus 1/2 I parentheses v over r parentheses squared equals mgh. And since a spherical shell, it's I equals 2/3 mr squared. I plug that in where the I is.
Okay, that's what I did too. So I ended up getting mgh equals 1/3 m, and then in parentheses wr squared. And then I canceled out the mass on both sides. So I ended up, when I like isolated it all out,
Yeah.
I think that's not, yeah. I got 1/3 v squared equals gh. So then I did 1/3 and multiply by 8 squared equals 9.8 h. And I got 2.17 meters.
7 meters. I did something different
Okay, what did you do?
because there's the 1/2 mv squared plus the 1/2 times the 2/3 mr squared. By distributing things, I came out with 5v squared over 6g equals h.
Okay, what did you end up getting as the height with that?
So with that, I got 5.45 meters. Because in part B, what I got in part B by using the 1/2 mv squared equals mgh, switching it over, I got 3.26 meters after plugging everything in.
Okay.
So knowing that treating the ball with this, so you're treating it as it's rotating up, and then the next as if it's sliding up.
Yeah.
And so if it's rotating up, it's supposed to it should be farther than if it's
Farther.
just
Yeah. That makes sense. All right. Okay.
So
And there's another equation for the rolling up, isn't there, right? So you just use that other equation if it's rolling instead of sliding.
I'm trying to remember. I believe so.
I have it written somewhere. I can go back and find it. But that makes sense. I mean, what you explained was like almost identical to what I did, but you adopted it for sliding instead of rolling. All right.
Yeah.
You can just use your number 5.
Okay.
Your number 5, and what was the other one? Your number 3?
3.
Yeah,
5
we
and
prepared on those. Okay. For 6,
oh,
we're calculating the moment of inertia. So I took the equation PE equals KE, and then my KE is KE rotational plus the KE transitional. And then I made my PE just MGH.
okay.
And then I made my KE rotational plus KE transitional equal to MV squared plus IW squared over 2. So my full equation is MGH equals MV squared plus IW squared over 2.
Okay.
And then I isolated I, and so I ended up getting 2R squared divided by V, and then I multiplied that by MGH minus MV squared over 2. So the final equation I got was the I equals MR2, and then multiplied by 2GH over V2.
Okay.
Oh shoot, I had my calculation somewhere else. Let me go find that real quick.
Okay.
I'm
seeing that we're using the same thing, but we did it in a different
You did it in a different
fashion. So I'm trying to like follow.
Yeah, that's the hard part. Is it's like you don't know how somebody else worked their problem, so unless you can like see it, it's hard to look like figure it
Yeah.
out.
But for the most part, from what I'm following, it's the same.
How did you end up doing it if it's different than mine?
Well, it was just in a different way. So I used the KE1 plus PE1 equals KE2 plus PE2. But
Yeah.
the KE1 0 and the PE2 is 0. So you're left with the MGH on one side and the 1/2 IW squared plus 1/2 MV squared on the other. And then you have to transform it so you get into the MR state, MR squared.
Yeah.
So you plug
Yeah.
in the.
So I ended up getting I don't know if I wrote this down right, because I just have MR squared multiplied by 0.37 is what I ended up getting.
0.37.
0.037.
037. I got 0.0889 MR squared.
0.0889. The problem is like, I don't know for sure that I'm doing it right. So I don't know that mine is right. And then it's like, I can't see yours. So it's hard to know if yours is right, you know?
Yeah. Which makes it really tough.
I know. Cause it's like, I understand that the group projects help because you have someone else to explain it, but it only works until you can explain it to each other.
Right. The only what I have on mine after I told you about rewriting the equations,
Mm-hmm.
on the MGH side, I just have the M times the 9.8 times 2. And then on the other side is the 1/2 I,
Mm-hmm.
6 squared over R squared plus 1/2 M 6 squared. So that's how I wrote it out.
That makes sense to me.
What do you have? So I can try to understand.
I have 2 multiplied by 9.8, and then I multiplied it by another 2. I don't know where that came from. And then I divided it by 6.2 minus 1. 6.2, 6 squared, sorry, minus 1. But that doesn't. I'm not understanding where I got the second 2. Because it's the height.
Unless you multiply each side by 2.
I think that's what I did. But I don't know why. All right, let's go with yours because yours makes the most sense to me. Because like doing mine, I confused myself multiple times, but they made sense.
Don't you love it when they make sense?
Yeah, I know. It's always like, oh, I'm dead certain. Like the individual exercise I was working on today, I was like, I've got this one. It's easy. I've nailed it. We're done. And I was like, nope, you did it wrong 14 times. All right. For 7, for A, I said the mass goes down because he jumps off of the merry-go-round, and so that decreases the inertia, which will increase the angular velocity.
That's what I got.
For B, I said since he's jumping backwards, it causes an increase in the force, which increases the angular velocity. And then is that what you got?
That's what I got.
Okay. And then for C, I said since he's jumping like straight parallel with the axis, there's going to be no torque, like no change in torque. And so the angular velocity will increase without him on it.
That's what I got.
And then for D, when he jumps off, I said he's jumping off in the opposite direction, which will increase the force in that direction, which will increase the torque in that direction, which will counteract the velocity it's already have going. So it'll decrease the velocity.
Yep.
Okay. For 8A, I have the equation to get the angular momentum. I just have A equals inertia multiplied by W. And I converted the 6 revs per second into radians. So I did 6 multiplied by 2 pi, and then I multiplied that by 0.4. And I got 15.1 kilograms meters per second squared.
Yes.
Okay.
I put 15.08, but 15.1 is the same.
Yeah.
So.
Okay. For B, I have the inertia equals the initial W over the final W multiplied by the initial inertia. And so I have the 6 revs divided by 1.25 multiplied by the 0.4 from the previous, well, the moment of inertia, not the initial, by the previous inertia given in A. So I have 6 divided by 1.25 multiplied by 0.4, and I got 1.92 kilograms meter squared.
I missed a step in there. Yours makes perfect sense to me.
Okay, we can use my 8. It's time for me to contribute anyways. For C, I did alpha equals delta W over delta T. So I have 3 minus 6 over 15 minus 0, or just 15. And then I multiplied that by 2 pi over 1 rev. So I converted the 6 revolutions per second into radians. And that gave me negative 1.26 radians per second squared.
Yep.
Okay. And now we're on to number 9. Okay, I need to find a new piece of paper.
Oh, did you find the torque of that?
No, I did not.
All you do is times the.
I do what?
So all you do is times the 0.4 by the 1.26.
Oh, okay. So let me do
That's
that
it.
real quick and we can use mine. I don't know how my mind just like totally glossed over it.
That's what happened with me and B.
And
I found the radians per second, but I didn't find the rest of it.
I didn't know there was a part C. Sometimes it's hard if they're not like separated. Okay, for the torque, I got negative 0.504
Yep.
in M, right? That's the right numbers for torque.
Right.
Newton.
NM.
Yeah, okay. All right.
Wish it were M&Ms, but
Would make it a little more enjoyable.
yes.
All right. Let me see what this paper says for A. And we can take a look at it. Okay. So on the example they give, they made L is equal to L prime, and then they set L equal to IW.
Right.
I'm writing this down so we can turn it in.
Sounds good. So that means L equals the MR squared with V over R.
Yeah, that's what I just wrote. But then if you, I think you can just cancel out the R squared and the V divided by R, so you just get L equals MVR, right?
Right. That's
Then
what it looks like they did here.
I can't read this one part, so let me pull up in my lab again. It's blurry.
L prime.
Okay, so L prime is inertia prime W prime. Okay, I could not read that for some reason.
Oh, so that's supposed to be two other primes.
Yeah, I think so. And
Okay.
then they set
Which that is equal to
that in
MVR.
VR as well, right?
Right.
And then they make W prime equals MVR over I prime. And
Okay.
then, okay, so since we're using a rod, our inertia is going to be I equals MR squared divided by 3. We're using a rod, right?
It's a stick.
Oh, dang
It says stick on either one, but it
Okay.
gives thing.
it. Okay, then I think we're fine.
So that means inertia prime equals MR squared
And then
plus.
that would be the MR squared over 3, right?
Right. It mutes it or takes out the R because there's an R squared. So M plus
So M plus big M over 3.
times R squared.
Okay. All right. I think we're.
And
How much does this thing weigh?
so it weighs 50 grams.
Where do you see that?
And so it's at the top of the paper where it says example 10.15 rotation and collision. Suppose the disk in the figure 10.26 has a
Oh,
mass of 50 grams and an initial velocity of 30
for some reason, I
when
thought we were getting like different numbers. So, because this is literally just they've already done the problem for you.
right,
Oh, okay. Well,
which is
that makes
true.
sense. Okay, because I was like, I
The,
have no idea where they pulled this number out of.
what I've been trying to figure out is the 1000 RPMs and the 1.5 centimeters because all I see them use
50 grams and 30 meters per second and 1.2 or meters.
Because that's how long the stick is. I don't see
Yeah.
anything that deals with rotation or radius, really. Oh, because that one's still got it. Yeah, it's just the weights and the.
I'm still not seeing the 1000 RPM anywhere.
Neither am I.
It's not in any of the example. So why would they bother telling us the RPM if we don't need it?
Distraction.
They should not be allowed to do that because I can't keep up with it.
Just burn the papers now. They'll call it good. We don't need distractions.
Well, like, if I don't need it, can you just cross it out in a big black marker and I'll ignore it?
I'll make sure there's some glitter around a do not cross sign.
This is important.
Yeah. Basically, the answers are all from the example. There's no. Because all it is after that is you plug and chug it.
Yeah, I know. I'm trying to find where they put in the 1.5 as well. Because I used 1.5 in part C, but I here they have 1.2, but I don't know where the 1.2.
But the 1.5 in C is the kilograms times meters per second. And so that's not even centimeters.
But this at the beginning of 9 it says in which the disk originally spins clockwise at 1000 RPM and has a radius of 1.5 centimeters. So I use that in part C, but I think I needed to use the 1.2 because that's how long the stick is.
I'm trying to see where you did that in part C. Move, speed, gather somewhere.
I did mine a little different than the book because I didn't realize the book was giving you the answer. So I don't know that I did that right.
I don't see. The only time I see them using a 1.2
is the very, very last step. And that's where I
of
in
A.
mine, yeah. And I got the right.
That's for the stick, not the disc.
Oh, yeah, that makes sense.
So they're giving us information about the disc, but all we need is the stick.
So this one we just need to plug in different numbers.
Well, I'm not seeing a place to plug in different numbers.
I know. I think it sounds like they just want us to repeat it out and make sure we understand it. Because it just says repeat example.
In which the disc.
Yeah. Oh yeah, I know. But I wanted to ignore that.
It doesn't make sense throwing that in.
I know. I don't know where that's supposed to go.
I'm going to keep looking here a little bit.
I mean, we can email him, but every time I email him to help me with a problem, he confuses me more. Or like I have to exchange like 4 or 5 emails with him, and then it makes sense. But I have a feeling like I'll email him and he'll be like, "Well, talk to your group member." And I'll be like, "But I did, and we both don't know."
If you want, I can just shoot him a quick email right now.
Yeah, we can do that. I mean, this isn't due until Thursday, right?
Wednesday, I thought.
I think labs are due Wednesday and group work is due Thursday.
Oh, yes.
Yeah.
Sorry, I'm kind of a day ahead, so sometimes I
know.
get mixed up here.
It's okay. I don't know. What do you
Yeah,
want?
you're right. You're right. I'm getting way ahead of myself.
That's okay. All right. So, do we want to send him an email and ask, and then just whoever sends the email can turn it in, I guess, because they can get the answer for 9, and then Does that make sense?
That does make sense.
Okay. So we said that you were going to send problems 3,
And
5, and 6, right?
yes.
Okay, so I can do the 1 and 2 and all of 4, and then I can do 7 and 8, and then I can email him or you can email him. What would you rather do?
I am fine emailing him.
Okay.
He
So
hardly hears from me at all, if at all.
he hears from me a lot. I don't think he loves that. Okay, so I'll send you photos of my work that's not number 3, 5, and 6. And then you can turn in 9, 6, 5, and 3. Yeah, that splits it pretty evenly, right?
Yeah, that's actually
Okay, so I'll send you those photos and I'll send you the link for the video. And then
okay.
just when you get an answer back from him, finish number 9, and then make the PDF.
Sounds good.
Okay. All right, we'll do that.
Sounds like